first, I will just start sharing my introductory slides here. And okay. And let's also wait for more participants. Helen, how many people do we have on YouTube?
So far, 11 people watching.
11 people. Okay, so we can wait maybe 1 or 2 minutes.
Sure.
Okay.
Yeah, Professor Vedral. So just a quick question.
Yes.
Yeah. So there are some list of open problems in IQ, QCI Vienna web page. So is this problems related to those one, or this is the new one?
Good question. I'm not so sure actually what they wrote today. I don't think what I have to say is necessarily in the conventional list of open problems. I think I will probably spend a few minutes at the beginning to maybe comment on exactly this.
Yeah, thank you. So I am posting that link in the chat box.
Very good.
All right. So Helen, I think we can slowly start. So maybe let's start recording. Okay, perfect. So the meeting is now recorded and we can officially start. So hello, everyone. Welcome to the next meetup organized jointly by Quantum Computing Group from Washington, Toronto, and Warsaw. My name is Pavel Gora. I'm the CEO of the Quantum AI Foundation, and together with Dr. Sebastian Zając will be the moderators of this event. And we have a pleasure to host a great speaker, Professor Vedral from the University of Oxford. And today he will give a lecture about some open problems in fundamental physics. So as you can see, this meeting is recorded. So hopefully the video will be later available on our YouTube channel. And if you have any questions during the talk, we've agreed with Professor Vedral that you can raise your hand, you can interrupt and ask your questions so that this talk will be more interactive, hopefully. Before we start, we would also like to announce some of our next meetings. So next week, Dr. Clark Alexander will give a talk about painting quantum pictures with walks on graphs. Then in 2 weeks from now, Jitesh Lalvani will tell about quantum for space, application of quantum technologies for space. Then in 3 weeks from now, Dr. Jacqueline Mathers will tell about GDS Factory and open source Python flow for circuit design, verification, and validation. Then in November, Jerne Rudi Finsgar will tell about new approaches to near-term quantum optimization. And then in December, Tim Linke will tell about gaming for quantum literacy, modern approaches to quantum information advocacy. And in 2024, so it's already 3 months from now, Dr. Krishnan will tell about accelerating materials discovery with AI and machine learning. We would also thank our partners and sponsors who help organize this event. And yeah, we would also like to congratulate the Nobel Prize winners in physics, of course. So the results were announced this week. And with this, I think I can stop sharing my slides. And Professor Vedral, if you're ready, the Zoom is yours. You can start sharing your screen. And thanks for accepting our invitation. It's our pleasure to have you with us.
Thank you for inviting me. Of course, it's nice opportunity to talk about something that I frequently think about, and I think it probably provides most of the motivations for my research. I will let me spend a few minutes explaining the kind of issues I have in mind here. So I think we, in my abstract, I used Lord Kelvin, who basically, at the turn of the last century, he gave this famous address, at which he was trying to anticipate the future of physics at that time. And he kind of presented a picture of an almost complete understanding, other than two clouds, as he called them, on the horizon. And it's very interesting that, of course, one of the clouds, as he called them, turned out to lead to relativity. This was the cloud. I think the way he put it is the inability to detect motion through ether. That was the Michelson-Morley experiment, of course, and related the many. The other, he barely spent any time on this, by the way. He mentioned the cloud, anything about it. What he spent most of his time talking about is the other cloud, which was the inability of classical physics to explain heat capacity of various objects at that time. And of course, we know now, I mean, the reason for this was the fact that the equipartition theorem, the famous result of classical statistical mechanics, that every quadratic independent degree of freedom gets half kT, if you like, of energy in equilibrium, is simply not correct. It's correct at high enough temperature, Maxwell-Boltzmann distribution, but of course, as the temperature goes down, you have to take into account the quantum particle statistics, and so basically, in his address, I think Kelvin managed to anticipate both of these revolutions. And the question that I want to pose is, are we now in a similar position? I think we are. You know, you basically listen to all sorts of people making all sorts of comments about the future of physics and why is it that we haven't had a new theory for over 100 years and so on. And I think it seems to me this is largely because of the lack of really experimental need to do that. Unlike the two problems that I think Kelvin found very easy to identify at that time, and they really were experimentally clear, however, they couldn't understand them theoretically. I feel we are in a similar position now, and those are the kind of issues that I really want to talk about. So let me go onto a very brief summary of these things. So obviously, physics is full of open problems, and not only is it full of open problems, but it's hard to tell. One has to engage in some kind of intuitive guesswork. It's hard to tell which problems will turn out to be fundamental. We don't know. I mean, that's the whole point. If we knew about it, we'd all be doing it, and we'd all be working on all of these issues. However, I think it's clear that certain issues are more likely to be of the type that will be resolved already with our existing understanding. So for instance, you know, if you're talking about high temperature superconductivity, I'd be very surprised if this led to a genuinely new type of a theory. It's possible. It's possible that it will overthrow quantum mechanics and we will really have to come up with a different theory to explain this phenomenon, if it exists at all. If it didn't exist, of course, it would require a new law of physics to explain why this cannot be done, or someone would have to prove this within quantum mechanics. But my bets are that this is really a standard solid state / engineering kind of problem. I don't think we're going to learn anything fundamental from that. And of course, there are thousands and thousands of problems of this kind. So I think each of us has a certain intuition, I suppose, as to what we think will ultimately be quantum, what will ultimately force us to somehow modify either quantum or general relativity, or both. Of course, it can happen at the same time, if you like. All of these are options there. Now, quantum gravity is an obvious question, and I think it's not even exactly clear. One can, of course, give a whole talk and a sequence of lectures on this topic alone. But the reason why I'm putting this is because I want to talk exactly about this and related problems, is that this could signal to us a more generic issue with the way we understand quantum field theory. Quantum theory applied to continuous systems. Now, and I think, again, a bit like Kelvin, I mean, and this is my area of expertise. I will spend a disproportionate amount of time talking about this. I think this is the area where we are going to violate general relativity within the next 5 to 10 years. So in the lab, this is why I think these are also superior findings in physics usually, if we really can engineer something in the lab that tests our basic understanding. And the reason why I'm saying this is I want to contrast this with the other open problems that you may hear about related to this as well, which are the issues that come from astrophysics, astronomy, from dark energy, dark matter. These are wide open issues. Like I said earlier, it's not obvious to me whether these are fundamental problems. Ultimately, it's not obvious that they will turn out to be fundamental. They could, and in fact, either of the two could really force us to modify either the standard model, the quantum mechanical, again, field theory, or general relativity, or both. It's possible, but I think the observations in the macro domain are far less robust, as far as I'm concerned, of course, than anything that we can really do in the lab. So I'm kind of putting all of these issues in the lab ahead of anything in astrophysics. And to me, this is basically the most exciting thing about the current state of affairs. And then, of course, people talk about even bigger questions, which are the origin of the universe, the long-term future of the universe, the end of the universe, and so on. And of course, these are exceedingly difficult to discuss, especially if we think that our understanding of the fundamentals is really tentative. So unless we are kind of a bit more confident that we have a good theory that accounts for both micro and the macro phenomena, it seems to me it's very difficult to ask these questions, or it's not difficult to ask the questions, it's just difficult to give reliable answers. One can almost maintain any answer that they want to have and defend it quite intelligently, simply because the observations are almost non-existent there, almost non-existent, basically. So either our observations will have to improve, and of course, or we will have to somehow have a better inclination about the foundations of physics from other corners and angles. So that's kind of the thing that I want to talk about. And
Okay.
To put it into, please interrupt me if there are any questions.
Yes, there is a question from George on our chat, so maybe it's good to ask it. Is there a clear definition of a fundamental problem, or is this only realized with hindsight?
A great question. Yeah, I think it seems to me that it really is only ultimately realized with the hindsight, like I said, because even in Kelvin's case, I think the two clouds that he identified could have simply turned out to be resolved within classical physics. And had that been the case, we would not be talking about them as revolutionary at all and leading. So by fundamental, I really mean that these are questions whose answers will force us to modify our basic theories. They will really force us to come up with a new theory that obviously, as in the past, will reduce to the old theories in certain domains, just as quantum mechanics reduces itself to classical physics in certain domains. However, I think this theory must really tell us something new in these areas where we are questioning it. It seems to me very difficult. You know, one can have good arguments why some things are more likely to lead to something fundamental, to a new revolution. But I think, in all honesty, it's difficult to give a 100% answer. It really is difficult. It's kind of, you know, one has a feeling that something is more fundamental, and that's what I'm going to argue here about. But I don't think you can ever really prove anything like that. I hope that. Please ask me more questions.
I think we can continue. George
Excellent.
said just thank you for the answer.
I noticed Dr. Dax has a question.
Yes. Yeah, there is a question from
okay.
Soumya, so maybe Soumya can unmute himself and ask.
Yeah, Professor Vedral. So, as a researcher, so which type of problem we should focus? Like, there are some problems that we cannot experimentally verify, as like string theory, or should we focus some of the problems that can be experimentally verified, not today, but say near future, say 10 years or 20 years?
Great. I think, yes, I think it's a good point. I will be advocating exactly this second kind of problem. And I want to show certain areas where I think we can already start to ask these questions. I think, of course, that's not to say that it's not worthwhile investigating theories that go well beyond this. So I'm not against that at all. And I think, as we know in physics, certain ideas take much longer to mature. So I think that's fine as well. However, I think if you want to focus on the immediate future, and it seems to me that we are at that stage, then I would be looking for really questions that can be answered in the laboratory. And I think those are the most exciting questions. And I think it's possible, like I said, that some of the things we can already do now will inform us how we need to modify both GR and quantum mechanics. So to me, that sounds extremely exciting. And so let me give you a little bit more of an intuition how I see it. This is a very superficial and very brief introduction into quantum mechanics and what I think it's telling us about the world. And the reason why I'm saying it this way is because I think that the way that we understand the theory naturally then informs us what kind of questions to ask. So I will give you a very brief summary, which and outline a few key points that I think quantum mechanics tells us. So on this slide, I'm simply saying that quantum mechanics achieved a huge conceptual unification. Because as you know, in classical mechanics, we either dealt with particles, what Newton would talk about, or with waves, a standard theory, you know, like electrodynamics, of course, or water waves, sound waves, any kind of waves. And those were thought classically to be two different kinds of entities. And then, of course, with quantum mechanics, everything really became a wave, became a quantum wave. And there was this unification of these things. And I think that the messages that come from that. So, you know, there's quite an intricate kind of a beautiful history of all of this. But the people that I have in mind in this line of thought are people like Darwin and Mott and Schrödinger himself, ultimately, who were dissatisfied with with the language of quantum jumps, discontinuities, and things like that. And they argued that it's perfectly consistent to think of everything as a wave, and that particles simply emerge in this wave-like picture through interaction between different waves. So the experiment I have in mind that illustrates this the best is this decay of an alpha particle. And I think this was a huge debate in the early days of quantum mechanics. You know, why does quantum mechanics claim that alpha particle is a wave? Actually, it's a spherical wave that's emitted from the center here of decay, if you like, and it should spread isotropically, completely spherically symmetric in all directions. However, if you look at the cloud chamber results, what you will notice, of course, is that each alpha particle leaves a straight line track. And of course, as you do this experiment many times, all sorts of tracks will appear, just like on the left-hand side image here. So, and then people like Darwin and Mott and Schrödinger simply explained that you can use waves that are applied to alpha particles. You can treat the gas in the cloud chamber also as a quantum mechanical wave. And then through the interaction between these two waves, we actually have the particle tracks emerge in a certain well-defined limit. So basically, you know, if you think of the first alpha particle as being emitted as a wave, then the first molecule of this gas that it hits and ionizes and it creates a small cloud that's visible to us defines the position of the alpha particle at that point. And then, of course, with an overwhelmingly high probability, the next molecule of the gas that it will hit will be along the same line, and so on. So you can basically explain the emergence, if you like, of classical Newtonian kind of like behavior, but by treating everything in the universe, in this case, the alpha particle, the gas, even the observer, if you want to, by treating them all quantum mechanically. So in that sense, it's a perfectly consistent view. And here is the list of things that I think are extremely important. And it's precisely by pushing these kind of questions further and further that I believe we will be testing quantum mechanics and possibly then arriving at something else that may come after quantum mechanics. Of course, no one has any idea what this might be. But the beauty of this picture is that measurement is simply just the creation of entanglement between the observer and the system. The observers themselves are nothing special in this picture. They're just quantum waves like any other physical system. And they have no special property, no necessary additional special property to be observers. So you can think in this cloud chamber, you can think of the molecules inside the gas as observers of alpha particles. It's perfectly valid, even though these molecules are relatively simple objects themselves. They are as simple as the alpha particle itself, if you like. In this case, it's really completely immaterial whether you call the gas an observer or you call the alpha particle an observer and the other one is the system. It's completely democratic as far as quantum mechanics is concerned. So there are no collapses, there are no quantum jumps, there are no discontinuities, there's no spooky action at the distance. All interactions take place locally, just as they should. That nothing violates. Please do ask me a question.
Yeah, Professor. So, if the observer means you are telling that living observer or non-living observer. So, are these two are same?
Great question. Actually, I think that's another domain in which I think we will be testing testing some fundamental ideas. At the moment, I'm not making any distinction between living and non-living. I don't think that a living observer has any extra properties that are relevant for this kind of thing. Of course, living observers are different to non-living entities. However, I think as far as the quantum measurement is concerned, what we call a quantum measurement, what we call the creation of entanglement between the system and another system, if you like, it makes no difference to me whether they're living or not living. That's a great question, actually, because frequently we end up discussing questions whether quantum mechanics also becomes relevant for living systems. I think it's a great point. I won't probably say anything about it in this talk other than what you just asked me now.
Okay. Thank you, Professor. We have 3 other questions. Maybe I will ask 2 of them now because they also seem to be related to this slide. So the first question from Barry, in the universal quantum slide, so this slide, how does this point of view get rid of actions at a distance?
Excellent question. Actually, that is you are anticipating my next slide, I think, and I will answer it in the next slide. I think the important question there. So far, I talked about the wave mechanics, and I talked about the picture that we naturally associate with Schrödinger. The key ingredient that's required for your question is the contribution of Heisenberg. And it's actually, the question is really, what are the underlying elements of reality? And by answering this the way that Heisenberg answered, and maybe I will delay my answer because I will show it to you on the next slide, you will actually realize that you don't need to have action at the distance. So I will clarify this on the next slide.
Okay, so maybe I will ask one more question now.
Please
question from Dev. Nowadays, there is a lot of criticism of Big Bang theory by static theory supporter. Is it true that static theory supporters are neglected by top-tier scientists as reported?
Oh, good question. That's a good question. I really wouldn't know about it because I'm not familiar with that much with that community. I don't understand the kind of the social dynamics that you're asking me about. However, I should say something very general. And this is that, of course, science is done by humans, and obviously all humans are subject to fashions. This is true in any field, and it's possible, and it's well documented historically, that because of certain fashions, some things, for instance, took longer to realize than they would have taken otherwise. So it wouldn't surprise me at all that that certain focuses in science, I think this includes certainly the early universe and many other questions, are influenced frequently more by the social dynamics of the community than necessarily by the experimental evidence. Because like I said, the experimental evidence is very scarce. There isn't much of it. It's difficult to have very strong views scientifically if you're in that position, that you really have to acknowledge that you don't understand many things. So as far as I'm concerned, the origin of the universe is certainly wide open. And it seems to me that the focus will possibly be changing and people will be exploring a wider range of possibilities. But whether that's really stopping us now, I can't answer that question.
Okay, that's good. Thank you. So
I have also a question, Pavel, if I can.
Okay, so yeah, go on.
Yeah, so my question will be, as I understand the measurement, we can also understand as a just kind of interaction. So we have interaction that do not produce entanglement between the systems. This is the first. The second point is that you say that, as I understand, you say that we can treat physical objects like wave, like a true things on our universe, and we can describe by wave everything. But So if waves are truly elements of reality, why we have a discrete spectrum like for observables? Because even from quantum field theory, we know that okay, we use kinds of waves and fields, but they are not classical fields and classical wave. Yes,
No,
so
they are not.
So we cannot say that because in my opinion,
Yes,
this point of that we have particles and wave is just a classical point
no,
of
I
view.
mean
And
it quantum. I mean it quantum mechanically. I will answer it on the next
yeah,
slide.
okay,
Your second point is clearly the case. What I want to advocate. The first point is also very important. By measurement, I mean any interaction which can generate any amount from 0 to 100% entanglement. All of these I would qualify as possible measurements. This includes what people call POVMs, generalized measurements, weak measurements. Any of this stuff is simply explained as an interaction between two or more physical systems. So all of this is allowed by me. I allow exactly what you said, that you can have a state of the system and apparatus which goes from one product state into another product state. Doesn't have to have entanglement, and you can, as you say, call this a quantum measurement as well. That's all allowed.
Okay, thanks.
Okay, so I will also allow Dave Chapman to ask a question because he previously asked a question on YouTube. So Dave, please go ahead.
Of course.
And then we'll continue.
Yes.
The quantum computer technology allows us to easily provide different types of Bell states and sophisticated entanglement situations.
Yes.
Do you think that this is going to be useful in either testing these theories experimentally or in getting clues to find out answers?
Yes, great point. I think that's the beauty of somehow technology and the fundamental science working together hand in hand. It's an excellent point, because the quest to make a scalable quantum computer really is related to testing quantum mechanics in the macroscopic domain, and of course beyond certain size of these computers, exactly as you indicated, will be able to prepare more and more intricate states, which are really genuinely quantum mechanical and as far away from any classical description as we can think of. And the question really is whether these states are accessible to us. I think this is definitely intimately connected with the fundamental questions that I want to raise. I have a very specific one in field theory that I will get to, but I think there are other questions along these lines, and I think our technologies will be very important in that direction.
Thank you.
Okay, good. All right, I think we should go ahead. So I know that there are many other interesting questions, but we can come back to questions later.
Excellent. So this is a final ingredient, if you like, which is exactly as you pointed out, that these are not, of course, classical waves. We cannot explain things with classical waves. They are quantum waves in the sense that what does the waving are what Dirac called quantum numbers, not classical numbers. And I think this goes back to this question of spooky action at the distance and things like that. These things only enter if by reality you really mean reality described by real numbers. If you think that the fundamental elements of reality are still real numbers and they're really sitting out there describing locally the properties of systems, then we know through various experiments that this cannot be held together with relativity. We have Bell's inequalities and all sorts of other inequalities that we know are violated in more or less all systems that we've been able to test so far. So the underlying, this is telling people like me, and I think it's telling most of us, that the underlying elements of reality simply cannot be real numbers. They have to be more complex entities. And the person who in fact invented quantum mechanics or discovered quantum mechanics by thinking like this is Heisenberg. I mentioned Dirac, who may have given the clearest exposition ultimately, but it was really Heisenberg. And here is how Heisenberg would talk about alpha particles behaving like particles, even though they are waves. It's a very interesting, very simple calculation. So I think the ingenious thing about Heisenberg was that he said the following. He said, you don't need to modify classical dynamics. Leave all classical equations of motion intact. Newton's laws stay as Newton's laws. Maxwell's equations are Maxwell's equations. It's just that the entities in these equations are simply not numbers. They are no, you cannot maintain them anymore as numbers. And I'll give you a very simple, I think this is an example that we could have all understood at the age of 14, probably. It's a very, very simple one, where you have a particle, think classically at the moment, a free particle, there's no forces acting on that. It's traveling at some velocity v. And you're talking about a position at the time t, which of course is equal to the position at the initial time, whenever it is that you label the t0, plus of course the velocity times the time. And now the ingenuity lies in which of these things, they're all real numbers, of course, in classical physics, but which of these things should become quantum numbers? Which of them should be upgraded to operators? That's the question that Heisenberg really asked. And that's his first paper. It's written in a very confusing way for various reasons. I think he himself was not even aware of matrices at that time, of linear algebra that much, and so on. So he was really making things up as he went along. Probably one of the most creative physics papers of all times. Anyhow, if you upgrade positions and the velocity, momentum, but not time here, that's interesting, of course. And you can immediately say, why not time? And we can get into that discussion as well. It's one of those fundamental questions. But if you upgrade the positions and the momentum, and you take the commutator between x0 and the left-hand side, and the initial position x0 and the right-hand side, what you will get is that the left-hand side gives you the commutator of the position at time t and the position at 0. And here we're using the commutator between position and momentum, which is simply I times h bar. And because I have velocity here, I have to divide by the mass of the particle. And then we know that when we have a commutator of this kind, it implies automatically Heisenberg's uncertainty relation. And the relation now said, this is what Heisenberg, I literally just stole this from Heisenberg. I'm not doing anything original. The implication is that the spread in the position at times t, delta x at t, times the spread at position at time 0 is greater than a certain bound which grows linearly with time. This you would have seen, and you would have called it spreading of the wave packet, but it's normally done in the Schrödinger picture. It takes a bit longer to derive it. Still a simple calculation, but here it's really obvious. It's exactly telling you what you need to do. And look, you can express how it grows, the spreading of the wave packet. And then what Heisenberg would say is that the alpha particle gets localized by the interaction with the cloud, and then it starts to spread according to this law here, simply because it's described by Q numbers, by quantum numbers. It's a wave, but it's a quantum wave. It starts to spread, then again, it collides with another molecule of the gas, gets localized, and then again, it follows this free particle dynamics. It's a very similar relationship to what you would get from simple diffraction. I think this formula I wrote here is simply a very simple formula from wave optics. that we all learned about, the distance that the wave travels, the wavelength of the wave, the size of the aperture, and the size of the spread, if you like. And they're all related in this very simple way. But Heisenberg taught us that this comes from the fact that the underlying elements of reality are not numbers, but they are what Dirac called Q numbers, quantum numbers. They are operators, they are observables, as we call them. They are matrices, call them whatever you like, in whatever representation. But the key property is this non-commutativity. And that's it. So basically, if you list all of the things that I wrote before and add this as a postulate that the fundamental elements of reality are Q numbers, that pretty much captures how we understand quantum mechanics. And it consistently describes everything that we've seen so far. But I think what it's telling me is that we should push this even further and explore whether there are more things that we should think of as quantum, and then really subject this to test in the lab. And that, I think, will get us somehow to an interesting set of questions in fundamental physics. And I think this is something that seems to be becoming, with our developing technologies, closer and closer to reality. We really don't need to be asking just questions about the origin of the universe or the dark energy and matter. We can already start to ask some very fundamental questions in the lab. So that's what I want to basically proceed to tell you about. But maybe there are questions already about this as well.
All right, let's see if there are questions. There is one question from Soumya, I believe. He raised his hand, so Soumya.
Yes, Professor, you are telling that so reality is described by like imaginary numbers. So, but after the measurement, we only get like real values. So, can we think like measurement is a process that converts some imaginary world to the real world, or?
I would say it's all sitting in the correlations between the Q numbers that arise during the process of measurement. And so you're quite right that what we observe ultimately in this picture are real outcomes to our measurements, whereas the Q numbers they are not just imaginary numbers, but they're tables of numbers. The key property is not that they're imaginary. The key property is that they don't commute. They cannot be simultaneously specified, if you like. And these real numbers arise simply due to the correlations that get established through interactions between these quantum waves. So that's kind of the picture that I'm advocating, fully quantum. So what that means is that, and I think that's what Mott and Schrödinger and Darwin all concluded with this alpha particle experiment, is that when you see alpha particle going in a certain direction, what it means quantum mechanically is that there is another branch in which the alpha particle is going in another direction, and yet another branch with yet another direction, and all of them exist simultaneously within this kind of quantum description. So I think this forces you to acknowledge that if everything is quantum, then somehow everything can be interfered in the quantum, at least in principle. In practice, of course, these things get harder and harder. And we don't know if we're going to have the resources to interfere really genuine macroscopic large systems, like living systems, for instance. We still don't know that. But what I'm assuming is that quantum mechanics, if it applies to them, then I think that this is the picture that comes out of it.
Yeah, thank you.
Thank you.
Okay, I think we can move on. I don't see more questions now on the chat.
Great. Let me continue with this story, because what I always found interesting, and I'm going to go into some of the things that I think we can test, and to me they sound very exciting. But this was Dirac's insight as well. He came into quantum mechanics from non-commutative geometry, by the way. So it's because he attended a set of lectures about non-commutative geometry, that this gave him an idea. I'm no historian of physics, but I read this somewhere that this is how it went. And if you think of these properties of straight lines classically, so of course, if you have a particle that travels in a straight line and another particle that travels with the same speed but starts from a different point, then of course they will describe their own straight lines, but these two straight lines will forever be parallel. If you plot them on the X and T diagram, they will never cross one another. And that's this famous property of Euclidean geometry, if you like. However, if you think of these straight lines described algebraically the same way, however, the coefficients in these straight lines are not just real numbers, but they happen to be these non-commuting matrices, Q numbers, then of course, in this kind of geometry, your parallel lines, if you like, can in fact intersect. And that's exactly the point in quantum mechanics. So basically, if you have here, I drew a very simplistic picture of two particles which are starting from different positions, and they can start with the same velocity. However, as we've seen, each of these particles will spread. So in a sense, if you put a detector here in this region, it is possible, because of the spreading of each of these wave packets, it is possible to get two clicks in that detector and detect both particles there, which would kind of be the quantum mechanical intersection of these two straight lines. So it's very interesting how somehow you can think of quantum mechanics geometrically. I mean, this is a nice picture, and I don't want to make this into something more fundamental than what I just said. However, it certainly challenges classical physics, not just algebraically, but of course, also geometrically. And I think this ought to be like this, ultimately, if you think really about it. So now, when we switch on the interactions between these particles, and that's going to be really something that I think we ought to be probing more.
Can I make one remarks about this picture?
Of course.
Because it's very hard to say that quantum mechanics broke Euclidean geometric, because it is hard to say that we have any geometric for non-commutative.
I agree. I agree with that statement too, because in a sense, the message is more that we shouldn't really be talking about these trajectories of particles at all, because they don't really exist, as we know. That's the point.
This is very tricky. That if you have commutative numbers or operators like functions, you can derive exactly from representation theory, exactly classical physics on manifolds. So you can have geometry. In quantum mechanics, because you don't have this commutative, you cannot derive geometry, and this is the reason. Why,
yes, I agree, and I think it's wrong. Even the spirit of what I will have to say from now on also goes in the same direction with GR. In fact, I will think of it simply as just another interaction. And I will focus on that aspect rather than the geometrical aspect, which I think actually misses the point as well. But I just think it's an interesting, more like a historical quirk that it seems that some of these pioneers of quantum mechanics came into it from non-commutative geometry. Certainly was a surprise.
I think that this point of view that from that. Heisenberg rules and non-commutativity is exactly fundamental things in physics between what is classical theory and what is not classical theory.
I agree with that.
And I just one remark: it's nice to see that statistical theory is commutative physics and commutative part of all this. So
Yes, you're right. And this would be a little bit how we think about it in quantum information as well. You're right. How does a classical world emerge? And I think it's exactly as you described it now. Great. So along these lines, when you now, I talked about three particles, but when you turn on the interaction, of course, I'm talking metaphorically, figuratively. You don't really turn anything on. They're always there in many ways. Sometimes, of course, you can engineer them to become stronger, weaker, switch them almost on and off, and so on. But the corollary of what I've been saying so far is that whatever mediates this interaction between these quantum objects must also be quantum in a consistent description. Now, of course, we have to test this experimentally, and ultimately maybe we discover something even beyond that. But what is clear is that you cannot have a proper quantum interaction between proper quantum objects that's mediated only classically. Exactly as you said with the elements of reality, if you like that language, which are fully commuting. So if you could entangle two genuine quantum bits, let's call them quantum bits, it suffices that they're just two-level systems, then whatever it is that mediates this, it could be a field, it could be another quantum system, doesn't have to be a continuum at all, ought to have, if you like, the same information processing power, the same degree of non-classicality as the systems themselves. And that's the interesting thing. And that's really the idea that I think we ought to be testing more, simply because there are many questions that I can think of that really rely on this kind of logic. And so I want to get into that exactly and discuss a few of these. So in a very kind of almost semi-popular way, some people have called this property totalitarian. Totalitarianism in the sense that anything that couples to a quantum superposition must become entangled to this superposition. When I say must, I mean must within this global picture of quantum mechanics. I'm not saying that this will turn out to be experimentally the case with everything in the future. After all, we don't know. That's what I think we ought to be testing. But as far as quantum mechanics is concerned, it simply says, this of course is the famous Schrodinger's cat experiment, but many other related experiments that have been proposed. As soon as you have even a tiny microscopic system like an atom or a photon in a superposition, and as soon as you couple this to another system, whatever it is, to another atom, to a measurement apparatus, to a cat, to a human, whatever it is that you want to describe within this framework, all of these systems have got to become entangled. They immediately have the full quantum capacity of the initial superposition. And that somehow is of course, a very important principle in quantum mechanics. And I think that's the one somehow that we ought to be really taking more seriously and testing more extensively. So let me just give you a very brief, of course, the picture of the electromagnetic field is very simple. And I want to question some of these as well, ultimately. But basically, the way we understand this is that the electromagnetic field on the left-hand side of this equation is simply coupled to the currents. These are the sources, if you like. So when you put a charge in the electromagnetic field, then this charge itself generates the field, and equations of this kind, of course, you can do this dynamically as well, and the equation of this kind describes that. Now, if you think, and we know this, of course, that you can put a charge in a superposition, in fact, this goes way back to Heisenberg's logic, why we ought to quantize the electromagnetic field in the first place. If you have a charge in a superposition, of two different locations. The question is, what is the value of the field a certain distance away? And of course, the totalitarian logic that I just told you about tells us that we have to have an entangled state, that the charge in one place generates one kind of response of the field, in another place generates another response of the field, and they exist simultaneously in a superposition. So that means automatically, if I have any experimental indication that J is a Q number, is a quantum mechanical operator, then for consistency reasons, F, E and B fields, A field, whatever you want to use to characterize your electromagnetic field, must be quantum automatically. Otherwise, the equation, as it's written down, simply makes no sense. Semi-classical descriptions make no sense. They're just wrong, basically. And in fact, many of them we know we can prove wrong experimentally. And that's kind of what I'm advocating now. Let's push it even further. In gravity, it's the same story. And I think that's the theory that's going to go first. Classical GR will simply be invalidated exactly by the kind of logic that I'm advocating here. And that's something I'm probably more excited about than most. So you have, again, a very similar field equation that the energy momentum tensor, somehow these are your sources, if you like, in GR, generate on the left-hand side the gravitational field. And if you do accept that the mass can be, and we know that the masses can be in a superposition of two or more different places, that automatically means that this G, whatever it is, must also be a quantum number, at least at some level. And I think we ought to test this at the lowest level of the theory. Already there, it's extremely exciting, what people call the Newtonian limit. So I want to show you this famous physics cube, which basically just tells you about physics in terms of the three fundamental constants: the speed of light, or in this case, 1 over the speed of light, because as speed of light becomes infinite, we identify that with classical mechanics at the origin here. Then, of course, the Planck constant h bar, and G, the gravitational Newtonian constant. And so basically, we haven't tested many, of course, we've tested many quantum mechanical properties on their own. We've tested many special relativistic and general relativistic properties on their own. But already when we are talking about a semi-classical part, and there are all sorts of predictions there, like the Unruh effect, Hawking radiation, all of these things are completely still inaccessible to us. In fact, we haven't tested that at all. And in this corner where all three constants start to matter is what some people might call a theory of everything that unifies all of them. We are, of course, very far from that. But what I'm advocating at the moment is simply to test this one of these corners, one of the vertices, where we are still in the kind of Newtonian limit of general relativity, but we are already asking quantum mechanical questions there. And the question is, will general relativity in this limit display full quantum mechanical behavior? My bets are yes, but someone needs to do this experiment. But of course, it would be interesting if it didn't come out that way. I'm fully open to that possibility. And in fact, in some sense, this would be much more intellectually exciting and challenging if it didn't come out the way that I'm predicting and that many other people would be predicting. So I've written a lot about this, and I think it's related. I don't want to kind of bore you too much with all of these questions, because what you're testing also is what some people would say is the equivalence principle in the quantum domain. The equivalence between acceleration and gravity. And so the question that you're asking at this level really is, if I have a mass in a superposition of two different locations, and I have a test mass at one location, a certain distance away, which way will this test mass go? Which way will it accelerate? And as you know, why this is particularly exciting is because there are physicists out there who are betting that the quantum mechanics will collapse at this level. So they're betting against what I call the totalitarian property. They are betting that this test mass will simply accelerate either towards one of these locations or the other, but not simultaneously in both directions, which is what I would be betting on. And I think quantum mechanics clearly states that this ought to be the case. So basically, in each branch, you satisfy the equivalence principle. And what quantum mechanics, this is true for any principle in quantum, the energy conservation, any conservation is satisfied exactly in the same way in quantum mechanics, branch by branch. And then you have a superposition of all of them simultaneously. So I think this to me is a hugely exciting question. And the way I would phrase it, rather than through the equivalence principle, and it's a paper that I wrote with Chiara Marletto, and independently Sugato Bose, and I think his colleagues came up with a related idea. The question is really, if we have now two superpositions of a massive object, and each of them generates this kind of superposed gravitational field, then is this setup capable of entangling these two masses simply through this kind of quantum mechanical gravitational interaction? And if you do show that they do get entangled, the masses, then this to me signals, in fact, and the papers I'm quoting are offering logic and proofs in that direction, signals the gravity really, at least at the Newtonian level, has to have non-commuting quantum mechanical, if you like, degrees of freedom. It's certainly non-classical at that level. It doesn't answer anything at higher levels. People always ask me, what about in the strong gravitational regime? I have no idea what will happen there. I can't tell you anything about it. I certainly can't think of any experiments in the strong gravitational regime of this kind, anything accessible. However, at the other end, in the weak gravitational limit, it seems to me this is a well-defined question, and it's really worth doing, especially that there are different people betting on different outcomes, and that sounds very interesting to me. So it would be just a picture of this to give you an idea. It's really it's one of those interferometers that we call a Mach-Zehnder interferometer, where you have a massive object being split through some kind of beam splitter. Probably some kind of electromagnetic field will do this job. Could be a Stern-Gerlach type experiment as well, where you are looking at the magnetic degrees of freedom and using the magnetic field to split this system into different spatial locations. And you have these two interferometers that each undergoes this superposed evolution. However, while they're doing that, they are also naturally coupled through gravitational forces. And like I said, it's enough to think of this gravity in the lowest, in the Newtonian limit of GR. And then because distances between these different arms of the interferometer are different, that means that the superposition of these two masses will pick up different phases as the masses evolve. And if you time this appropriately, and if you're interested, I can tell you about the numbers and what would suffice to do this, you could actually end up with an entangled state between the two masses. Entangled in the sense that if you measure one mass in one arm of the interferometer, you know that the other one is in a particular superposition. Whereas if you measure the other mass in the other arm of the interferometer, the second mass is in a different kind of superposition. So it's a kind of 0 plus 1 minus kind of state if you come from quantum information side of things. And to me, if gravity could entangle two quantum superpositions initially, two objects that were not entangled but were just simply in a superposition, then this would be a definitive proof that gravity at that level is really quantum mechanical, that we must use non-commuting observables to describe gravity. And this would invalidate classical GR. This would be the first proof that classical GR is not sufficient. To me, this sounds amazing, and whoever does this for the first time will be a hugely exciting experiment. I know that there are a number of groups racing, and I think it's doable. It's something we will have within the next decade, if not earlier than that. So this to me sounds interesting. Very fundamental question. What's going to happen? And like I said, I'm betting on quantum mechanics prevailing here. However, it would be even more interesting if it didn't. Then we really wouldn't know what to do. Like I said, semi-classical descriptions are very inconsistent because you have equations that are coupling quantum mechanical numbers, quantum mechanical operators to classical numbers. And it's not even clear what this means. It just looks inconsistent. All sorts of things go wrong when you have these kind of semi-classical descriptions. You are violating energy conservation. You're violating the second law of thermodynamics probably as well. All hell breaks loose if you have something like this, which is why it would be interesting if we were forced into something like that. I don't want to speculate about what it is that would not commute and so on. And these are all the things that we would discover. But let me say a few final things about this, and then maybe we can have a little bit more of a discussion if you're curious. The crucial tricks, if you ask me now, why is it that no one has been asking these questions before? Partly the reason is experiments, that we simply didn't have experiments that were good enough to probe questions of this kind, of basic interactions. How do these basic interactions work? Which aspects of the basic interactions are definitely quantum mechanical, and questions like that. And among the tricks that I have in mind, certainly the tricks that no field theorist is aware of. Maybe some of them have learned it by now, but traditionally they don't think like this. The tricks are what I would call local tomography is one of them. The fact that when you have an entangled state, you can make local measurements independently on each of the parties to reconstruct the full state. You never need to make global measurements. You can only do local measurements, compare the data classically, and basically that's what we call the principle of local tomography. And it's very interesting. It's counterintuitive that quantum mechanics satisfies this principle, especially because people always talk about quantum mechanics as being non-local and so on. And suddenly, you can actually estimate the full entangled state by making measurements locally on particles. You never need to measure them together. Another trick in our trade is the phase kickback. And of course, that's used in this gravitational experiment as well. Namely, the fact that if you have an entangled state of two systems or more, and one of the systems picks up a phase, then that phase automatically reflects on the whole state. That's another feature of quantum entanglement. So basically introducing a phase in one qubit that happens to be entangled to another qubit changes the phase of both of these qubits when they're in an entangled state. That's what some people call a phase kickback. And these are interesting things because I think they allow us to even test some of the basic ideas we have with fermionic and bosonic statistics and things like that. I think lots of these questions, at least to my mind, are not properly answered experimentally. And we have a lot of mileage to gain by simply revisiting them within the current kind of quantum information understanding that we have. Then, of course, there is the no cloning principle, a little bit like the principle that plays role in this kind of Schrodinger's cat totalitarian property. Then, of course, various issues with entanglement, local operations, and so on. In quantum field theory, so these are the things that, of course, we would like to test ultimately. we are really basing everything on some kind of locality of interactions, on of course, compliance with relativity, on gauge invariance plays big roles there. Observables, Hermitian operators, there are lots of questions related to each of these. Should they be modified? How do we really test them, and so on? And I think somehow between these two slides, I can already anticipate a number of interesting questions that I think will become more and more relevant. And this is all, like I said.
Can I have questions? So, excuse me, can I have questions?
Yes.
Could you define what you mean entanglement at level of quantum field theory, not at quantum mechanics level?
Oh, great question. That's an excellent question in its own right, by the way, which leads to some interesting tests as well that have not been done, by the way. In quantum field theory, you have to switch to thinking of the modes of the field as your fundamental entities. They are your subsystems, if you like. Particles are simply, as we know, excitations of various fields. They are not, so why am I saying this? Because you don't need two or more particles to have entanglement. You have the phenomenon that some people call a single particle entanglement. Sounds weird. How can you have entanglement with only one particle? What is it entangled to, if you like? But the key thing in quantum field theory is that the modes are your subsystems. They are the ones that become entangled. And the single particle is simply degrees of freedom within these modes. So for instance, if you have a single particle that's superposed between two spatial locations, a little bit like what I've been using in all of these experiments, in quantum field theory, you would call this state an entangled state. And that's because the modes, the spatial modes, which this particle occupies, you can think of the state of them as zero, meaning no particle is there, 1 + 1, 0, if you like. It's an entangled state. However, you have to now be able to execute the appropriate measurements in order to convince someone that this state is entangled. And while this has been done with a single photon, it's actually never been done with a single material object. We've never done this with a single electron, or let's say single atom, or anything like that. And I think these would be highly exciting experiments as far as I'm concerned, namely probing really this question of should we be thinking of the modes as the ultimate carriers of entanglement? And is it therefore really appropriate to call even a single superposition of a single particle? Is that actually also an entangled state? And that's something I've been advocating as well, that superposition and entanglement are really one and the same phenomenon. It's a very good question, actually, and I'm grateful that you raised it. It's not something I was planning to talk about, but I think this question too is a very interesting question.
Thanks. So I understand vacuum in quantum field theory is
that's it.
And entanglement states. Okay.
That's it. That's exactly right. So somehow you're testing. It's another very important point that you are making, that you are ultimately testing the reality of the vacuum and the fact that the vacuum state is just as good a state as a single particle or multi-particle states. I think that's a very important question. Again, I know a number of my colleagues who would, in fact, challenge this notion. They would think that not getting a click in your detector is not the same kind of a measurement as getting a click. I disagree with this, but I know that there are people who think like this. So I think that's a very important point as well. Yeah.
Professor, I can see that there are a few other questions. So now the question to you, would you like to answer now, or it's close to the end and we can wait?
It's almost close to the end. Why don't I actually give you another thing that I have in mind, which kind of is maybe the most general of these questions, and then we can go into a discussion a little Is that okay?
Yeah, I think it's okay. So yeah, let's
Brilliant.
continue, and then there will be Q&A session at the end.
Brilliant. So basically, this is a question of these ghost modes, as they call them in quantum field theory, and they're required if you want to give a causal, local and causal meaning that nothing propagates faster than the speed of light, if you like. The way we understand this is a little bit what I alluded to. And I think this is something that would be important to test. Namely, the fact that when you put a charge, here I'm using electrons, just to communicate to you the fact that even in quantum electrodynamics, some of these basic questions have not really been addressed experimentally speaking. So one way of talking about this is really to engage all four modes of the vector potential, to quantize each of them. This goes back now to my statement that if you quantize something consistently, you must quantize all the degrees of freedom. Otherwise, you're going to run into some kind of issues between sources and fields. And so the way we understand this is that what we call the scalar, the temporal mode, gets excited when you put a charge into a certain location. And of course, if you put a charge in a superposition of different places, then you're exciting simultaneously, according to quantum mechanics, you're exciting simultaneously this temporal mode in the vicinity of one charge, centered around one charge, and in the vicinity of the other charge. And of course, the way we understand coupling between two charges is that each of them now generates this kind of field. They affect one another, and somehow, in some limit, this is how we explain the electrostatic forces. And I would like to really have a similar experiment to the gravitational one, which also tests ideas of this kind. So is the story that we are telling ourselves really of this kind? Is this the full description of the static forces? And remember that this is how we explain forces in all field theory. I'm just using QED because I think it's the best understood, and we are all more familiar with this than in any other force. But I think any force you take within the standard model, and I was arguing gravity ought to be like that too, should be understood at this level in the same way. And why is this interesting? Well, it's interesting because exactly I want to just jump straight into this experiment that I have in mind to test this idea. It's interesting, first of all, because in some gauges, if you take the Coulomb gauge, for instance, the Coulomb gauge would deny the quantum reality. It would, in fact, would deny the classical reality to some degree as well of the modes, like the temporal mode that becomes important here. So the longitudinal and the temporal mode in the Coulomb gauge are called non-dynamical degrees of freedom. You don't put hats on them, you don't quantize them, you don't think of them as quantum numbers. However, if you do think of them as quantum numbers, you seem to be getting a different prediction. And I find that hugely interesting because whatever textbook you open, people say that all gauges are indistinguishable and should lead to exactly the same prediction. And yet here, I'm telling you about the simplest experiment I can imagine. And it seems to me different gauges are giving me different predictions. And that to me sounds mind-blowing. So, which one is right? What kind of explanation is the right explanation, even for static forces within quantum mechanics, within quantum field theory? That to me sounds mind-blowing. And I think we ought to be testing. So what is it that I have in mind? If you make a superposition of a single electron, then each of these positions creates its own electromagnetic field and gets entangled to it. So if you look at the superposition of the bare electron, if you like, at these two places, it ought to be not maximal simply because it's entangled, if it is, to the scalar degree of freedom, to the temporal degree of freedom of the electromagnetic field. And that's the question I'm asking. Is this true? It's true in the Lorentz gauge, which is the one where you really acknowledge the reality, the quantum reality of all four modes of the electromagnetic potential. However, a Coulomb gauge person doing this calculation would say, no, this entanglement doesn't exist there. The key trick to testing this is to do local tomography here, not to close the interferometer. This is why I think field theorists have never thought about this. It just doesn't occur to them that anything like this is possible. They don't think about quantum physics in its full generality and beauty. They miss these points. They miss these simple tricks. So the trick here, so to speak, I mean, it's a challenging experiment, is really to estimate the degree of the superposition of this electron without closing the loop. Because once you close the loop, these two states of the electromagnetic field also merge back into the same state, and you will recover the full interference. And we know that. We have electron interference, we have electron tunneling microscopes. All of this is confirmed beyond any reasonable doubt. We know that we can interfere these objects. However, what I'm claiming here now is that if our understanding of the electromagnetic field is fully quantum mechanical, then there is a limit to how much you can interfere even an electron in two different spatial locations. And this to me sounds incredible that we don't have an answer to this. Which way is this going to go? And it's very interesting. Again, I'm betting that it will confirm that we need to quantize all the degrees of freedom of the electromagnetic field. But I would be more surprised and more excited if this wasn't the case. It would really be telling me that these gauges are somehow not really equivalent to one another. And we need to think harder how to describe even the basic fundamental interactions. It's very interesting. And here you can do a very simple calculation to even estimate the degree of entanglement. It's a very tiny amount. You can amplify it by using larger charge, by using, for instance, 10 electrons. Of course, the experiment then becomes much more challenging to coherently superpose 10 electrons in one location and 10 electrons in another location. But the question is, would the local tomography then tell you that this superposition is actually due to the entanglement with the electromagnetic field? This sounds to me like a very interesting question. And I think the answer, again, I'm betting, like I said, will be that the electromagnetic field will have to be quantized in a particular way, and more degrees of freedom than we are conventionally thinking ought to be really quantum mechanical. So that's the spirit of this, that we really push quantum mechanics as far as we can, and then hope that something at some point will really go wrong. And I think sooner or later something will go wrong, and then we will have to think about what comes next. I don't want to, like I said, I want to really, I don't want to raise too many questions here, and maybe some of them will occur in our discussions. But I think just to go straight to the conclusions, that as far as we can tell, quantum mechanics really applies to all objects at all scales. We've tested it up to certain scales. We haven't tested it that far, but we have no reason to suppose that it will fail. However, that seems to me the right direction to test. It's the direction our technologies are also taking us in. And the question is whether this will continue like this as we quantize more and more things. Now, I want to close with a similar statement that I started with, which was Lord Kelvin betting on these two clouds, or saying basically everything is well understood other than the two clouds. We, of course, have no idea what the two clouds are. There may be more than two clouds as far as we are concerned. But certain things could surprise us. I mean, I'm just saying here things like, if we discover that there is no dark matter in the same spirit that there is no motion through ether, and these kind of further quantizations that we need to do in order to account for certain things could count, for instance, as two clouds on the current horizon. But I think my conclusion would be that even within the lab-based physics, we don't really need to go into the macro domain and ask these big cosmological questions, which certainly are even less clear. I think even within fundamental physics, we are now reaching this limit where we are starting or are able to start to ask these questions. And this to me all sounds very exciting, because I feel that it will force us to reconsider how we understand even the standard model. Thank you for your attention.
Great. Thank you, Professor. Thanks for this great presentation. And I can see that we have several questions already. So let's start the Q&A session. And Soumya, maybe you can start. You can unmute yourself.
Yeah. Thanks. Thank you, Professor, for this excellent talk. So
thank you.
Thanks a lot. So I have a question related to the single particle entanglement. So yeah, so when first time we heard this thing, this also seems to be weird. So just from an application point of view, so can we make something useful using this single particle entanglement, like or can we do like this CHSH test or some version of that, or some useful, you can say, protocol that or this is like a only theoretical concept?
No, it's an excellent question. Actually, when I've written about these things, I really had some useful applications in mind, of the kind quantum teleportation or entanglement swapping, also for communications. The key thing ultimately, I think you alluded to it as well, tests of the Bell or CHSH inequality. Yes. Because they're all related, of course. The set of things you must be able to execute in order to confirm, let's say, Bell's inequalities is virtually identical to the gates you need to be able to do to teleport, for instance. And I think the difficulty is exactly, think about it this way. Think about a single atom which you've made in a superposition of two different spatial locations. And now you want to be able to treat each of these as an independent physical subsystem and make measurements on one of these spatial locations and the other. The tricky bit is the following. The easy bit is, of course, to confirm correlations of particle numbers. That's obvious, because if you get a click that the particle is in one place, you will simply not get a click that it's in the other place. So they're perfectly anti-correlated, if you like, 0, 1, and 1, 0. What you must have on top of this, and this is the tricky bit, is a complementary observable. Remember, it's all about Q numbers ultimately. So you must be able to measure in a basis which is a superposition of the vacuum state and one particle state. And this is a difficult one. It's difficult because what you need is a quantum reference with respect to which you want to confirm this superposition. And in my proposal, for instance, I was thinking about Bose condensates as doing that. So I'd be thinking of a single particle which is superposed, but it's sitting somehow in a background of possibly even two different Bose condensates, one in one location and one in the other. If you can do that, and I think there are people that actually can even do something similar experimentally, then you have the full spectrum of things that you can make this entanglement into as useful as any other entanglement. They are much more challenging experiments than the photonic ones. The single photon experiment is, of course, much easier to do. And all you need is local lasers, really, as your local references. For material, for atoms, you need condensates, and that's the difficulty, but it's doable. And I would like to see this experiment ultimately done as well. But I think it could serve technological purpose too.
Yeah, so Professor, I have a simple confusion regarding this. So suppose, when we wanted to teleport, say, particle C, so what we have normally, we have particle A and B. So we take Bell measurement with C and A, and we get the unknown state of C to B. That's all. So for single particle measurement, so particle is either A or in B. Suppose we do a Bell-state measurement on A and C, then there is no particle on, say, B. So how this state can be teleported to somewhere where there is no particle?
It's an excellent question. Actually, it goes back to the heart. It's an excellent point. It goes back to the heart of this idea that it's the modes that are your subsystems. So here you really wouldn't be teleporting necessarily a particle. Because conventionally what you do is, you are right, what you do is you think about the internal state of the particle as your quantum degree of freedom, let's say spin up or spin down or any superposition of the spin. But what you do really is you teleport the whole particle, so to speak. In other words, you take the state of that particle and imprint it on another particle that's far away. What you're doing here with a single particle is you are imprinting the state of the mode in one location into another mode, which should have the same capacity, at least, as the first mode at a different location. So you're absolutely right. If you had a superposition, for instance, of different particles in one mode, then this teleportation would allow you to have a superposition, the same kind of superposition, whatever it is, in a different place. So you should be switching from teleporting the state of a particle from particle 1 to particle 2 or particle 3. You should be thinking, I'm teleporting the state of a mode, which could involve any superposition of the vacuum and different particles from one location, from one mode into another mode. That's the key idea.
Right. Yeah. So that is fine. And then we can apply.
And by the way, sorry, this contains your question as well. If you really insist on teleporting the state of a particle, then no problem. Then you just need to involve more than one particle. That's also true in this picture.
Yes. Thank you. So here, in this picture, we are then allowed to make some unitary transformation of on that mode also, right?
That's it.
Right. Yeah. So, just a last question of this continuation. So is there any experimental evidence of this theory, or it has not been?
Only with photonics. I'm only aware of photonics experiment where a single photon has violated Bell's inequalities in this type, but no one has done anything with let's say atoms or electrons or whatever other material particles. That's why I think it would be hugely exciting. I've discussed this with various people who I think may have the technology, but no one so far has done it yet.
Okay. Thank you. Sorry for this long.
No, not at all. It's good. It's a good point.
Okay, good. So, Eric, maybe you can ask your question. You can unmute yourself. Eric?
Oh, okay. I'm trying to get everything working here. Start video. I performed these experiments. I performed the single particle entanglement experiment with both gamma rays and alpha rays. And so it's the beam split coincidence experiment. Is my video? No, it's not. I want my video to be.
I can, now I can see you.
You can see me?
Yes,
all right.
I can see you now.
All right, so I did it with gamma rays and alpha rays to do the beam split coincidence experiment. I think this is the experiment you want. And so I get the opposite answer than everybody else. It should go one way or the other. And so what I do is I compare to chance. And I do a delta time histogram. So the previous experiments that have been done, it just gets a band of noise for when it goes click there or click there in time. And so I see this great big peak where it goes together in time more often than accidental chance. So I compare to chance, and I get big numbers, typically 20 times chance when I do it with gamma rays. So, and no one, like you said, no one has done it except for visible light. There are problems of doing this experiment with visible light, and I've identified that. So with alpha rays, it looks a little bit different. I have, it's similar to what Rutherford did, where anyway, there's two detectors that face each other, and there's a gold foil in between, and the alpha ray should go one way or the other. And so I compare to chance on that as well. And I've seen that do 6 times accidental chance. So it's the loading theory. I'm going back to Planck's second theory of 1911. And the way it works is continuous absorption and explosive emission. That the emissions are quantized, the absorptions are thresholded. And you don't know the difference between thresholding and quantizing unless you know how to see through this illusion. And so I figured it all out. I did this experiment many ways and times. I've done this experiment since year 2001. And you could see it all on my website. I have a few websites. I call it the threshold model, the way it works. So just look up, type in threshold model, one word, .com, and you'll see all my experiments.
Yeah, let me just make a, I will definitely have a look at it. It sounds very interesting. Let me just make a comment that what is important in the idea that I've been proposing is that when you make a superposition, I really want to avoid having to re-interfere. So I'm trying to avoid a closed interferometer, in a sense like a Max. I don't want a Mach-Zehnder interferometer. I want an interferometer where once I've created a superposition, I now proceed to completely locally interact with each of these arms of the interferometer.
Right. That's
so
right.
I don't want to scatter them back and
that's right.
That's the key thing here.
Look, I'm not putting it back. I'm just doing the simple beam split experiment without reconverging the two beams.
That's it.
Right. It was earlier done by Clauser, and then Aspe and his team.
Yes.
And there are problems with the photomultiplier tube, the way they interpret it. Anyway, when you do it with gamma rays, you get around those problems. And I've done it with several different radioisotopes, different kinds of gamma rays, and different detectors to try to see if I had some artifact, different geometries. I've done it 100 different ways.
I will have a look at your site and read it. That sounds very exciting.
Yeah, right. All right. I do hope you get back to me, and anyone can find me through just looking up my name, Eric Reiter. I'm in Pacifica, and I'm about to put out a book on this. Well, you can find it. I'm easy to find. I'll let you go.
Excellent. Thank you. Excellent. I put it down. I've got you now on my web, so I'll definitely check it.
Thank you.
No, it's all.
Great. Thank you, Eric, for asking, and thanks, Professor, for the answer. Sebastian?
Yeah, at the beginning, thanks for a very interesting talk. I have 1,000 of questions and thousands of things, but maybe to be short, At the beginning, I want to go to this problem with this gauge. I see just two solutions of that.
Yes.
First is bad computation, which I propose to check. And the second is that maybe the difference is not because changing of gauge, but in other kind of gauge, you can, because quantum electrodynamics is computable because of tiny these tiny numbers of constants. Yes, so you can compute loop to get correct results. So maybe this is problem that this approximation on some levels are not the same. But if you do more approximation, more loops and more calculation, you will get this correction.
Yes,
okay,
I'm completely open to that possibility, that ultimately they ought to give the same answer, and that would also sound logical to me.
Yeah, because this is one of logical, because it should be independent of the gauge.
Yes, I agree with you. That's my intuition too.
Yeah, and
it would be really weird if they didn't give the same answer.
Yeah, and the next things was that you told about Q numbers, about these operators, and one thing I think that one place where we have this because you said about interaction, yes. So how we describe interaction? We describe interaction by potential, yes, and this potential is always classically, even if you describe it by operator. Why classically? It's because it's dependent only on the difference of the position. So this is the reason why even if we have quantum theory, we effectively describe it by some classical part of interaction. And I think this is the place that we should look better. And the third thing is that many kinds of people think that quantum computing can help us with quantum field theory and quantum gravity. It's very nice to see this. But in my opinion, it will be better if we construct quantum computers based on quantum field theory than quantum mechanics, because they are nearly the same, but on theoretical level they are not the same, and there are a huge gap between these two theory. So of course I very appreciate that I can be here and touch this quantum gravity, because there are a lot of things that we can speak about in this topic. But thank you very much, and
yes,
just my remarks.
No, thank you for the comments. I think they're very important comments, and in fact, you're right. What I was talking about are probably very specific experiments that didn't really go into fully utilizing the computational capacity of the fields. Certainly worth thinking about how to make a quantum. I think that's a beautiful question in its own right, and I understand what you mean by having some advantages in doing that. I think that's an important question in its own right.
Thanks.
Okay, good. Thank you, Sebastian, and thanks, Professor, for answering. Do we have more questions?
Yes, I see Ron has a question. If it turns out that gravity is based on particles, graviton, why couldn't there be counterparts, pushtons?
Sorry, that second, if gravity is based on also on particles, let's say gravitons, then what is the conclusion?
Let me say it, since Helen, this is really kind of a silly question. If it turns out that gravity is based on particles, let's call them gravitons, why couldn't there be counterparts? We could call them pushytrons. And if a pushytron exists, what does that do to the whole issue of dark matter and dark energy and essentially all of quantum mechanics?
Right. So the question is more like you're talking about some kind of anti-gravity, right?
Yes.
Yeah, I don't know. Certainly, you know, whenever you're discussing the conceptual coherence of your theory, like quantum mechanics, I don't think it necessarily runs into difficulties with anything of that kind. You know, people talk about the fifth force. I think the beauty of maybe some of these simple experiments that we can do is, in fact, that we can test the same principles with whatever the claim is, whatever may exist there. So, you know, if you say, oh, there is another force, and I think it acts like that, then it seems to me the same experiment ought to somehow be able to, let's say, entangle genuine quantum bits by using that force and things like that. I think otherwise the question is, you know, the formalism is agnostic about that, certainly. I mean, you have to find the evidence for these things from other sources. And maybe, as you said, if we require this for the expansion of the universe and we need to explain this in some way, maybe there is an extra force that does that. And there are all sorts of speculative ideas there. So I agree with you. This certainly doesn't say anything about your question. Incidentally, it doesn't even say anything about gravitons, really, because you're not measuring them directly. You could have a Newtonian part being really quantum mechanical without necessarily ever talking about individual gravitons. That's the nice thing. So you're not even confirming gravitons, really. You're not disproving them. It's not against it, but in a way, you would need to work harder in order to really probe gravitons in the same way, for instance, that we can do tomography of the electromagnetic field and confirm photons and so on. So there are many questions of this kind. Certainly nothing wrong with what you're suggesting.
Thanks for the response. That's actually amazing.
All right, great. All right, I see that that Soumya has one more question, but maybe someone else would like to.
Can I ask questions?
First?
I'm sorry,
Yes.
My name is Gaetano. I just
Go on.
maybe philosophical question, not exactly physics.
Yes.
Several years ago, there was a researcher at the Imperial College in London, was a physicist, and he conjectured that the laws of physics may not be totally invariant. And I wonder if that's the case, that the laws of physics are dependent on the state of the universe, then some of your fundamental problem that you highlight in the summary at the beginning may not be solvable. So I wonder what you think about that.
Oh, it's a very good point. I wouldn't agree that they wouldn't be solvable. It would require certainly a change of attitude, as you said, because indeed, the way that we've been thinking about it and the way that I talked about it is that the laws of physics are there, they are time independent, and we are really, as we dig deeper, somehow we discover more and more accurate laws. However, it could be, as you say, that the laws of physics change with time, that constants, for instance, I think it's an old idea, by the way. I think you mean Magejo, Jean Magejo. I think I know who you're talking about. He made it super popular and I think in the public domain. But I think the idea is an old one, that the laws of physics may be changing or constants may be changing. And I think it's possible that this is the case. What I think, the reason why I think that this wouldn't invalidate anything is that it would simply force us to look for that law that governs the change, if you see what I mean. So that would be the thing to discover then. You know, if for instance, the equations of motion are the same, however, some of the constants have a temporal variation, then I think that's exactly what our experiments should then try to get at. How do they vary with time? What is the law according to which they vary with time? Why is the law like that? You know, is it compliant with quantum mechanics and things like that? there would be many beautiful questions in that direction. And I'm like most physicists, I would of course be open to this. I think it is a possibility. We don't know.
Yes, thank you. Thanks very much.
Okay, so Jordan would like to ask a question. Jordan, please go ahead.
Thank you. Fascinating. I have so many questions in these many different disciplines that this touches into. But the area that I'm working in and doing research in has to do with quantum information science and quantum computing.
Yes.
And specifically, you're bringing up things that relate to the data load problem. And we're dealing now here with not only a possibly different type of measurement, but measuring in a different way with the same tools to measure. But you're opening up two different things. Either way, whichever way this goes, you're opening up the possibility here and the bottleneck that we're having that we're needing to fix here. This has a lot to do with that. And where do you see things are in terms of movement of this? Are there people as excited as you and I in this? I mean, funding, where are we with all of this?
I think you are right that that as things stand, we don't really have a clear way to have a scalable quantum computer. All the indications are that ultimately we will have to engage in some kind of error correction. But then the problem is really the redundancy. You know, even in the most optimistic estimates, you need 100+ qubits, logical, let's say, I mean physical qubits in order to get one logical qubit out of it. So that doesn't look very optimistic at this stage. The claims, you know, the claims that various agencies make that they have 1,000 or 10,000 qubits are not really true. I think if you take the strictest definition that universality means that you ought to be able to execute any quantum, any sequence of gates, you ought to be able to prepare any quantum mechanical state, then I don't think that we have more than 10 quantum bits. We do have various ideas how to try to scale this up. And I think you're right, there is a bottleneck there that we don't know how to overcome. I don't know, I mentioned error correction, but of course, a thing that would help enormously is to have to be able to get rid of cryogenics, right? And be able to get rid of the need to really cool things down in order to eliminate all these sources of noise. So already someone coming up with a relatively stable qubit at high enough temperature would help, of course. That would already eliminate a lot of these problems. But I don't think we have anything like that at the moment. I'm optimistic simply because I see a lot of investment going into it, as you said. There is a great deal of investment, although what people are doing is more pragmatic frequently, that we're thinking, what can we do even with this small number of qubits? What if we integrate and have some kind of hybrid quantum classical and so on? It's not clear, you know, how quickly this will lead into if at all, into some kind of fully scalable quantum computer. I agree with you. So we're in a very kind of uncertain area now. I don't think we have an idea what the right technology will be, or what the right set of technologies will be. But I'm kind of optimistic that, you know, keeping the momentum there and lots of people thinking about these aspects, that ultimately this will, it still seems to be more like an engineering question rather than a fundamental question that we will really discover a law that will say you can't have quantum computers with more than 1,000 qubits. I don't think anything like that exists in nature. I mean.
Thank you. And where do you see a lot of the research happening? Are there hubs around the world that you see that are really active, like Caltech, their new center that they're opening up with the Fairchild, building that has the possibility for the multidisciplinary.
Oh, definitely. I think what made a real difference, as far as I'm concerned, and I don't know when this took place, maybe about 5 to 10 years ago, is that the industry started to become more interested and really excited about it. So, you know, with Google, Microsoft, IBM, all of these guys, Bell Labs are there. All of them really going in this direction. It seems to me it requires this kind of involvement and the know-how and the investment. I don't think individual academic laboratories, I don't think are able to realize this. We've already kind of made the transfer from universities into industry, and I think that was the key development there. But I think even industry needs help to do this.
Thank you again.
All right, Soumya, it seems that it's your turn.
Yeah, hi, Professor Vedral. So sorry, I have more questions. So
no worries. I might have to. I'm just looking at my watch now. So maybe around 8 o'clock, if we can finish within about 5 minutes, I don't mind at all, and I don't mind continuing.
Sure.
Later,
Let's
by
assume
email.
Yes, let's assume this is the last question now. And
excellent.
If there are any questions, you can contact Professor by email.
Yes, please contact me directly. I'm very happy to answer any.
Yeah. So Professor Vedral, so my motivation to do PhD was to understand entanglement. So I think we are all doing experiments and doing two-particle entanglements, and entanglement is a physical phenomenon, etc. But from fundamental point of view, from the creation point of view, so what makes actually two-particle entanglement? What is the physical process that, so we have two particles and we are doing some interaction and making them entangled. So what is the fundamental process actually happening there? So I did not get that. Actually.
Well, I think I don't, maybe what I will say will not be a satisfactory answer. And I understand that, because I think one should always ask more questions about the details of anything. But I think, as you know, at the moment, you're right. We need some kind of interaction. In quantum mechanics, most interactions, almost a random interaction, will ultimately give you an entangled state. So most interactions are really entangling interactions, and they have the capacity. So I guess your question would be more like, when we understand interactions the way we do, and let's say we write down Lagrangians, Hamiltonians, we couple Q numbers in a specific way, multiply them by some C numbers and so on, then maybe the question you're asking is, why these kind of interactions? Why do we? Because once you accept the way that we understand dynamics in quantum mechanics, then of course entanglement comes out very naturally out of that. You don't have to add it by hand. It just comes out of this formalism. And like I said, almost universally, almost anything you do between two or more systems is actually entangling. However, maybe the question you're asking is then really, why do we describe these interactions in this way? How do we know that they are like that? How do we know that they are not quantum mechanical, even at a more fundamental level, and so on, which is kind of what interests me. You know, when you look at the Hamiltonian and you decide to have some classical numbers there, like an interaction strength, for instance, then the question is immediately, why do you think of this as a classical number? Why is this also not a quantum number? In which case it becomes very interesting, you know, that you should actually start with a fully quantum mechanical model and then only derive certain limits in this way. And I don't think we understand this very well. Well, you know, what is the best way of doing these things? But I think entanglement, once you accept it, that somehow comes out for free.
Thank you, Professor. Thank you.
I think it's good to say that entanglement is property of quantum states, and not and just remember that states are not exactly the system. So it is not that you take ball and second ball, take them together and get entanglement. Yes, so this is on some different kinds of level than just maybe in mathematical way it's more simple say something about entanglement than saying how reality take this
yes, of course.
properties.
I mean,
so
exactly. Someone could even argue that we will never really understand. We have models that tell us how this works, but of course, how this really works in reality is yet another question. We shouldn't even confuse our models with reality, if you see what I mean. So I think it's a good point.
Okay, Professor. So we've agreed that the previous question will be the last one.
Thanks very much.
There's one more question on the chat from Dev, but Dev, please send it by email to Professor.
Excellent. Thank you.
And yeah, so with this, I think we can stop, and we would like to thank Professor Vedral once again for the great presentation.
It's a pleasure.
There are comments that it was a fantastic content, and I fully agree. We also enjoyed the discussions. So we'd also like to thank all the participants and hope to see you next time on our next Washington Quantum Computing meetups.
Thanks very much. Thank you.
Thank you.
Take care, everyone. Bye.
Take care. Have a good weekend.
Yeah, for the rest of you, if you want to stay to discuss, please feel free. I can wait.
So there was one more question from Dev, but I'm not sure, or maybe it was just a comment. Yeah, it was rather a question to Professor, but
yeah, I still have some time. If the participant want to stay to continue discussion, please go ahead. Yeah, if you want to take off, feel free. So no more questions?
I think that since the professor has left, then yeah, Jordan wanted to say something. Yes.
I don't know if Eric is still on the Zoom call, but I definitely want to read this. I have to absorb a lot of this, what you present on your site there in your forthcoming book. Sounds very, very interesting, and I definitely will follow up with you if I have some questions. But thank you for sharing that.
Okay. I don't see Eric here on Zoom, so most likely he has left. All right. Do we have more questions or comments?
Just thank you for organizing this type of talks, and really appreciate it. Thank you.
Okay, great. All right, I think we can finish, Helen. So we can finish recording. And yeah, as I said, we would like to thank once again everyone for attending, and we hope to see you next week, actually. So in October, we'll have meetups every Saturday. So let's meet again on next Saturday.